Okay, quick summary here. Trap graph for y equals x cubed plus 5. We've seen that graph. I'm extending the table for that graph with the idea of looking at the pattern of discrepancies between the average slopes and the slopes as predicted by the slope functions, which we call y prime, easily calculated if you know the rules, and our accumulated areas that would relate to the actual accumulated areas, the capital Y, fancy capital Y function, which is also easily calculated if you know the rules. At least for polynomial functions, the rules are quite simple. So these things are going to be easy to calculate, and we calculate the actual midpoint slope. Now, the actual midpoint slope means the slope at the midpoint of each trapezoid. So that the midpoint between 1 and 1.1 is 1.05. Here's the slope calculated at 1.05. And here is the trapezoidal approximation graph approximation to that slope. We see that these differ by only 0.0025, and 0.0025 is less than 1/1000th of either of these values. And of course, these values don't differ by much at all. That's why the discrepancy. So the discrepancy is less than 1 part in 1,000 here. Also, the discrepancy between the midpoint slope and the approximation is the same on every interval. Now, that's just a coincidence of the fact this is a third-degree polynomial making the slope function a second-degree polynomial, which has a derivative that's a first-degree polynomial that changes by constant amounts. And you can figure out what I just said if you know enough calculus. And if you don't worry about it. Okay, easy to calculate, though. Okay, and of course, since these values get bigger and bigger and the discrepancy remains the same, then these discrepancies are even less as a proportion of the actual value than these are. So the discrepancies here are less than 1 in 1,000. You get down here, they're less than 1 in 2,000, 1 part in 2,000. And I'm actually getting quite a bit less than that. So there are discrepancies, but they're small, and for most purposes, if we're using this to model something in the real world, these discrepancies become are small enough to accommodate whatever it is we're trying to accomplish, and we can use the trapezoidal approximations. There'd be no real reason to do so since the derivative function is easy to calculate, but for functions where that's not the case, we want to understand how these discrepancies behave. And then we do the same thing with the areas. Okay, we calculate the trapezoidal area, we calculate the actual accumulated area according to our antiderivative function, our capital fancy Y function, and we get these values that are, again, very close. Discrepancies here tend to stay around 1 in 1,000. Okay, in other words, the discrepancy is about 1 part in 1,000 compared to this. Okay, about 1/1000th of the actual values. So we have really very good agreement here between the trapezoidal approximation graph and the actual antiderivative and derivative functions. Now, that's not quite so true if you go to the right endpoint. In other words, we ask the question, does this approximation to the slope here hold over the entire interval? Well, I just looked at the right-hand endpoint of each interval, and I calculated the slope, again, using our y prime function, and compared that with the trapezoidal approximation, and found that you actually have a discrepancy of around 7 parts in 100. That would be 70 parts in 1,000. So the discrepancy gets much bigger if you go away from the midpoint. And we can draw a picture to see why that is. Here's a picture of a trapezoid and a curve here. And let's let that curve represent our function. Now, the function doesn't curve anywhere near that much on the actual graph, but I've exaggerated the curvature so that I can illustrate these discrepancies here. Okay? If we do a tangent line at the midpoint, which has a slope that is the same as the slope that we would calculate using our y prime function. In other words, evaluating the y prime function at the midpoint gives us the slope of a tangent line to our actual curve at the midpoint. And here's the slope of our trapezoid. Well, just looking at this, it all looks to make sense, and this looks like it's just about the same as this, even with the exaggerated slope and the exaggerated curvature. Now, there's actually some discrepancy, but this isn't drawn all that accurately. It's plausible that these two are very, very close together. It looks like they ought to be very close together, and that, of course, is borne out by what we see here. At the right endpoint of the interval, though, the slope has changed considerably on this exaggerated picture with the exaggerated concavity, and the tangent line at the right endpoint has a slope that makes a much bigger, a slope that differs from that of the trapezoidal approximation by much more than the slope at the midpoint. So the fact that this is 7 parts in 1,000, 70 parts in 7 parts in 100, 70 parts in 1,000, this is 70 times closer to the actual slope than this is. So that's something you want to think about and get a little bit of a feel for. Now, we move on after analyzing these discrepancies, and we asked, what's the effect of doubling or halving the increment? Okay, well, if we double the increment, that gives us an increment of 0.2 instead of 0.1. And I had that sketched here. You can see the purple segments that approximate the slopes. And you can kind of see there's still some purple left in this line and this line. Now that got somewhat obliterated when I cut the slopes in half. But if you just take the original graph, which was in yellow, and you can't really see it, but it had increments of 0.1, and double the increment, we get a trapezoid from 1 to 1.2, a trapezoid from 1.2 to 1.4. Now we also had our trapezoid from 1.4 up to 1.5, and yeah, not going to do anything with that. But what we've done then is this purple graph represents the trapezoid where the increment is 0.2. So we list the corresponding values. And I didn't list all the values. I didn't list all the rises, runs, and everything. I just asserted that when x goes from 1 to 1.2 to 1.5, still with the same function, y equals x cubed plus 5, these will be the slopes of the two resulting trapezoids. And the areas of the two resulting trapezoids are here. So the area of this trapezoid, the area of this trapezoid, here and here. So here are, actually I don't give you the areas, I give you the accumulated areas here and here. Here are the y primes at the midpoint, 3.65 versus 3.63, 5.08 versus 5.07. Discrepancies in the slopes turn out to be 0.01, and there's apparently some round off error here, or I just copied the numbers down wrong, but the discrepancies are going to be the same, and they're both going to be 0.01 between slopes as approximated and the slope of the actual function at the midpoint. And then between accumulated area of the trapezoidal graph and the accumulated area according to the ideal accurate function, we have these values and these discrepancies, and we note that these discrepancies are 4 times as big as these. And I commented, if you need to use a calculator to see that this is 4 times as big as this, you need to do some serious thinking about what you can do in your head. These numbers appear to be around or even more than 4 times as big as the corresponding numbers up here. This number is 4 times as big as this one, which is the bigger of the two numbers that would apply to this increment. In other words, we have 2 intervals of this trapezoid. Only the second, which has the greater discrepancy, would be as big as 1/4 of this one. And similarly over here. And without going into much more detail, we say that it appears that these quadruple, these discrepancies quadruple, and these discrepancies appear to at least quadruple. Now, we then went to a graph where we use an increment that's half as big as the increment we used in the original, so that we have x values 1, 1.05, etc., corresponding to cutting the trapezoid along the red trapezoids here, or cutting the graph, decomposing the graph, approximating the graph by these red trapezoids with half the increment that we had here. I didn't list all the values here. I've got dotted, ellipses, sets of 3 dots to indicate that there are values that should go here, here, and here in between the actual numbers that I've written down. But these are the numbers that we would get. The calculation is equally straightforward. And what we see is that the discrepancies between the slopes, between, again, the trapezoidal slope and the midpoint slope, become 1/4 as great as they were up here. Again, you shouldn't need a calculator to understand that 0.000625 is 1/4 of 0.0025. And these discrepancies between the accumulated areas also appear to become 1/4 as great as compared with our original graph. So that if we start with this graph and go to this one, our discrepancies become about 1/4 as great, which means we get 4 times as accurate. And if we go from here to here, we get 4 times as accurate again. So that cutting the increment in half appears to quadruple, or I say our own made-up word here, to fourple the accuracy of our graph. In other words, we go from 1 part in 1,000, let's say here, to 1 part in 4,000 here. And of course, there are changes. This goes to 1 part in 2,000 here, so this probably goes to 1 part in 4,000. The idea is that having the increment appears to quadruple our accuracy, to cut our discrepancies by a factor of 4. I'll comment also that in decreasing our trapezoidal width, the reason the areas increase more rapidly, in other words, that cutting the increment in half decreases the discrepancy between our trapezoidal area and our actual area, is simply that when we cut the increment in half, the little approximating segments get more than twice as close to our actual curve. So actually they, in a sense, sort of get 4 times as close to the actual curve every time we cut the increment in half, and that's worth thinking about.